Hope you folks had a great spring break. Welcome to EE 220-2 Hardware for Machine Learning. It's our great pleasure to have the D-Matrix team joining us and share with their latest technology in really thinking about hardware-software co-design for large language models, which is a very hot topic these days. And it's great to have, we actually have 3 speakers from D-Matrix team, so we'll actually get to see a broad spectrum of different things that they are working on these days. We have Steve Boja, close enough. Okay, good. Who is a co-founder and the CTO of D-Matrix, really focusing on how to do generative AI inference accelerators and in-memory computing. And Sudeep has a very successful career doing startups. One of his recent startup was acquired by Marvell recently, so congratulations. We also have Akhil Arankumar who will be joining us from Zoom. Good to see you, Akhil. I know Akhil for, I guess, a few years at this point. We overlapped also at NVIDIA, so it's good to see you again. Akhil is a senior principal software engineer at D-Matrix and is really focusing on software stack for the D-Matrix hardware. We also have Ayush and Kit. Okay, great. With the principal architect at D-Matrix, really thinking about how to accelerate AI inference with scale-out architecture. So we have a full spectrum of different hardware software components from D-Matrix, which is really, really exciting. And with that, Sudeep, take it away. We are excited to learn more about D-Matrix.
Thank you very much, Sophia. It's a real pleasure to talk to all of you and talk about some of the work we've been doing around large language model inference. Right. So this is sort of the outline of the talk. We're going to talk about characteristics of LLM inference, specifically around arithmetic intensity, and describe what we call like Corsair, which is the product name, solution to the problem. And then Ayush is going to talk about Scaleout. Scale-out architecture and algorithms. And then Akhil is going to talk about the software stack and specifically some ideas we have around KV cache and optimization of KV cache. So the metrics for LLM that matter are shown here. So the first thing is, of course, model quality. And model quality, so this is a plot from this website that tracks model quality based on GPT-4 as a reference. So that's 100. And then you can see where the other models come in, right? So that you have some of the proprietary models, the Mistral large, but then you also have some of the open source models, like the mixture of experts Mistral model that is actually competing with GPT 3.5. So you can see that the quality as measured by MMLU and a few other benchmarks actually exceeds what GPT 3.5 Turbo, which is one of OpenAI's more popular models, produces. And then it actually also beats the Google Gemini Pro. So the open source models now are catching up to a point where they're very competitive. Maybe they're not competitive on the latest and greatest model in terms of model quality, but they're good enough for many applications. So sort of inversely proportional to the model quality is the speed that you experience with the model. We call this tokens per second per user. So it's an interactivity metric, and essentially it's how many tokens do you see, right? If it's too slow and if it is something like 20 tokens per second, that may not be very fast, but some models do experience 115 tokens per second per user. Specifically, this mixture of expert model, and that's pretty good. So, and then you have price, which is what these service providers charge for 1 million tokens, right? And also you see if you want good model quality, it also ends up being very expensive, $15 per million tokens versus something like the open source models that are closer to 50 cents per million tokens. So eventually this price that the user experiences drives the models that are deployed. From the inference metrics, what matters is time to first token. So how long do you take before you start seeing any output? And then how many tokens do you stream in the decode phase? And we'll talk about the metrics a bit more. The total throughput also matters because you can batch a number of users, and that allows us to reduce the tokens per dollar, right? So those are the metrics that people care about. Our understanding from Sophia is that you guys already are familiar with transformers, but I just want to briefly talk about the token generation phase and the prefill stage. In the prefill stage, you have a sequence length of L, and the matrix dimensions of the activation matrices are shown below. So it's L times D. So whatever gems you're doing, so you do essentially most of the computations are actually in the feed-forward layer, the projection layers. There's about 8 D square worth of matrix parameters, and the D is very large, and then in the attention layer you have 4D square. So it turns out that you get a reuse of a factor of L in the prompt phase or in the prefill stage of the LLM. So you can these in the prefill stage, for example, you have a prompt here, and the model is generating one token by token. In the prefill stage, the computations tend to be compute bound, right? Because if you have a reasonably large L, then you have enough computations to do for the memory bandwidth that the architectures can provide. But then when you go into in the token generation phase, the query is 1 by D, so it's one token at a time. This doesn't include batch, right? So this is batch 1, and the key then and the values you try to reuse that and you save them. So that's the KV cache, and that tends to grow with the number of tokens you want to generate, right? But the arithmetic here is that these are all memory bound because you only have one multiply accumulate to do per user or per batch, and then the memory subsystems can't feed the compute. All right, so and the reason for that is Amir's plot here, that if you look at the latest NVIDIA GPUs, they've been able to push the compute up because transistors are still scaling, and they may dissipate a bit more power, but then people have better cooling techniques. And so for example, in the H100 Hopper GPUs have about 2,000 TOPS, 2,000 teraflops, right? But the memory bandwidth that Hopper provides is closer to 3 or 4 terabytes per second. So that ratio is the problem. The ratio is about 512. And what we just saw is that you have an arithmetic intensity of 2, right? Because they count multiply and add as 2 operations. So how do you utilize the compute when you don't have enough memory bandwidth? And the reason that both memory and the IOs don't scale is related to fundamental physics of driving IO out of the chips, right? So you have only so many pins that you can drive, and to escape that IO, you have to get the bandwidth up. In the Hopper generation, they go up to 112 gig, and in the Blackwell generation, 224 gig IOs. And when you go at that speed, because you have limited amount of pins to escape the IO, you end up with a fair amount of Nyquist loss, which you have to equalize, you have to apply forward error correction, people try to do pulse amplitude modulation. There's a fair amount of underlying technology to make the I/O work, and that tends to not scale as quickly because it's mostly limited by fundamental physics of transistor noise or signaling outside of packages, PCBs, and so on. And the memory subsystems are the same problem. So the GDDR memories are package memories that these GPUs used prior to them switching over to HBM, and you serialize up to 32 gig these days on GDDR7, and they are not exactly the same problem. And the memory DRAM subsystems are not very good at high-speed I/O, right? Because the DRAM processes are not tuned for high-speed I/O. So for that reason, there's been a push lately to put high bandwidth memory, which is in-package memory, and trying to provide more traces and lower speed signaling in trying to get the bandwidth up. So so that's what you see here. But the exponential trends remain, and certainly memory lacks compute, I/O lacks compute. So what happens because of this, right? Because of this is a plot from Databricks. So the x-axis is batch size, and this is what is called a roofline model, and the y-axis is throughput, tokens per second. So at batch 1, for example, you get very little throughput, and the compute system is underutilized because you simply don't have enough work to do, right? And then as you increase the batch up, you get better utilization, and up to a point where you fully utilize the compute, and that's where you enter the compute bound regimes, and so and then if you increase the batch more, you don't get any more throughput because you already saturated a compute. All you get is increased latency, right? So that's not so good for user experience. So ideally, you want to operate at the knee of this curve from a roofline model's perspective. So we're defining arithmetic intensity here. It's measured in flops per byte. And batch size is a lever to increase arithmetic intensity. In non-LLM inference, for example, computer vision, ResNet, and so on, there is nothing like a KV cache, right? It's only in LLM inference. So increasing batch size will increase the arithmetic intensity. And if you can find more users, you can always batch up more. But in LLM inference, it doesn't work that way fully, right? So the parameters are actually amortized. So if you increase the batch, you get more reuse, but also you have this KV cache problem, right? And the KV cache is growing per user. And so that doesn't help with arithmetic intensity. So what happens because of that is, so this is a plot of batches, right? So log scale all the way to 10,000 batch size. And these are different models. So the one at the bottom here is the original multi-head attention model. That's in this particular case, it's a Llama 7 billion parameter 4K context size, right? And what you see is a linear trend at small batch sizes because the KV cache as a percentage of the weights is still small. But then as you increase batch more, the KV cache becomes even more than the parameter count. So the arithmetic intensity saturates. And it's saturating at something like 14 here. And 14 is a far cry from 600, which is where the Hopper GPU sat. So regardless of how much you batch, the problem is extremely memory bound, right? And so people try to change the algorithm from MHA to multi-head attention to what is called group query attention. That is the Mistral model here, another open source model. And in the Mistral model, what they do is the KV cache is shared across a number of heads. It's what's called group query attention. So it's shared across 8 heads. And so you get better arithmetic intensity because KV cache is not growing as fast. So these are techniques to reduce KV cache. And then finally, there's bigger models like the Llama 70B, which is also a group query attention model. And then finally, there's a mixture of expert model, the Mixtral 8x7B, which is a mixture of expert model. And the mixture of expert model is an interesting model. It is more efficient to train, and more people are deploying these models, but it doesn't really help a lot in arithmetic intensity for medium batches. And most people want to operate in this, somewhere in the, if you're in the consumer space, you'll operate at a batch of 1, right? Because you're using your laptop and for LLM inference, and there's no one else to batch. But then in the data center space, maybe you can aggregate a few users, but it's hard to find a lot of users to aggregate. So somewhere between 16 to 64 batch size is interesting for us and for some of our users. In large consumer properties like OpenAI, where you might have 100 million users, you can probably drive a larger batch size than that. But most enterprise applications that have been fine-tuned don't have that level of user base to batch that much. Because of that, what happens is, so if you look at Hopper is right here. And the arithmetic intensity, the hardware accelerator, right? The ratio I talked about, compute to flops, and it doesn't intersect any of these roofline plots. So all of these models are memory bound. So the question we have is, can we build an accelerator that intersects this plot? And for that, that's the Corsair architecture that I'll describe, right? So this is a plot of late, yes.
So you mentioned your size is like 10-ish batch size.
Yeah, there's a range, maybe 16 to 64 or so.
I see. Could you provide a little bit more context why you think that's an interesting region, or what kind of user customers that you have in mind who want to use that range of batch size?
Yeah, so it goes back to queries per second and the number of users that they have and that the accelerator can support, right? So when you look at so the GPT-4 type of systems are running probably thousands of batch size, like 4K or so, right? They simply don't have 100 million users to saturate that level of batch. So in these applications, most of the time they struggle to find 16 to 64. It's primarily enterprise applications where you have some model that has been fine-tuned for some task, and in that task there aren't those many users to aggregate, but your system also has to deliver some amount of queries per second, and that distribution. So you can model it as a Poisson distribution, and based on those parameters, that's the range we come up with.
There's an enterprise application, but mostly for internal users that cannot reach like very high batch size.
Correct. Exactly. Yes. But I think the issue is more that even if you could reach a lot of batch size, even if you could reach 10,000 batch size, you still cannot saturate the compute, right? And by an order of magnitude, right? So this is a log scale that the application is such, the workload is such that you will end up with 10% utilization because you simply don't have enough memory bandwidth to feed the compute.
So this is also driven by the default, like picking this 10-ish range.
Right. So the 10-ish range is something that we can't, it's really what's coming in. But even if you could pick 10,000, let's say just there are so many users, it still doesn't intersect. So essentially, we have to figure out a way to get this, essentially get the memory bandwidth up. That's the fundamental problem that we are seeing. So this is a plot of latency versus throughput. And so this is latency that the user experiences on a log scale. So this is about 10 milliseconds or so. And this is a accelerator called L40S, and this is Hopper from NVIDIA, and this is for the 7 billion model. And what we want to see is, can we build an accelerator that can serve a lower latency and achieve a higher throughput? So if you can be to the left of this curve, top left, that's where you want to be, right? And so we'll discuss some techniques to do that. So primarily the issue is, like I said, is one of memory bandwidth. And the reason that it's very difficult to integrate compute and memory together. And so they tend to use this DRAM memory subsystems that have today in the Blackwell generations, they achieve 8 terabyte per second, but they do it at 4 picojoule per bit. So the total power in this is then 64 terabits times 4, 256 watts, just to read the memory and supply that bandwidth. And that's a big chunk of the power consumption of the accelerator, which is about a kilowatt or so. So 25% of the power goes there. You can put a lot of transistors and scale the compute up. So the Blackwell generation gets to 5 petaflops. But this ratio didn't change. In fact, the ratio might have actually gotten worse compared to what it was, again, because the slope of the memory bandwidth and compute are still not caught up, right? And so this ratio is 600. So can we find enough work for 600? So we call this the AI barrier. So the techniques we are working on is to integrate memory and multiply accumulates together, right, on the same something that can provide much higher bandwidth than what is possible with memory that's far away. So that's and then another way to solve this problem is through data types, right? So there is this data type called MX int8, which is a standard now. And this is integer data type, but that has a blocking exponent per block. So for every 64 blocks, there is a shared exponent. So in the regular floating point, you have an exponent per block, but a lot of the matrix computations are dot product computations, and the largest number is going to swamp everything else. So one format that is proposed here is this block floating point format, where you have a blocking exponent for some number of elements. In this case, it's 64, but you can choose the number of elements as a parameter. And there's different variants of this. You can make it 4 bits, or you can make it even floating point if you so choose. And these are the formats that people are using more often today. A blocking exponent along with either integer or floating point number within that block. So the data flow for our chips looks something like this. So we have an in-memory compute, which has the weights and the blocking exponent. And then you have an activation matrix that is stored in what we call a global memory. And that global, and I'll talk about that in a moment. And so you have a bunch of integers with the blocking exponent that feeds in as an input activation to the in-memory compute that has the stationary weights, and that gives you a partial products that is 30 bits here. And there could be multiple of these in-memory compute matrix multipliers that that essentially accumulate. So this is the partial product deduction tree that you're familiar with, and you get a 32-bit partial product numbers, and those are like those are no longer blocked, because when you multiply these two, each one has an individual block, individual exponent, and now you have a regular floating point number. So that's the matrix math, right? And then you will feed that into a SIMD unit, and the SIMD unit has a few different data types. You run a nonlinear function there, and then now you have to convert this non-blocking, so regular floating point, to a blocking format again. So there's some format conversion that happened on the fly, and then the NOC would then send that back to the input buffer, right? So that's what the data flow looks like. So that's a diagram of a chiplet. So we build these chiplets. Each chiplet has the notion of slices. So there are 16 slices here, and each slice has 8 of this. Each slice has two of these cores, and the cores have this in-memory compute unit that can do this matrix multiply with stationary weights, and then pass it through a SIMD engine that is attached right next to it, and there's a local interconnect and hierarchical interconnect and all-to-all interconnect, connecting all these slices so you can distribute the workload. And we use RISC-V to control all of these compute cores and dispatch the instructions. Right, so we have a hardware dispatch that because RISC-V otherwise would be overwhelmed. And we also have some interfaces, a couple of LPDDR interfaces to go to DRAM memory, and also PCIe to go to the system host. And then there's this chiplet interface called DM Link, which is a die-to-die interface that can push a terabyte per second of I/O to make all these chiplets look like a single chip. So what we do is we put 8 of these chiplets together on one package, and then we fully connect in an all-to-all manner 4 of them in this way. And so by doing this, we get the high memory bandwidth that we're looking for. We can support very large prompt caches. So we try to keep in this particular generation as much as possible inside SRAM memory, and so you will exceed the radical limits. So then you put many of the chiplets together and try to make it up by this interconnect topology. And then we have a low latency all reduce between all of these chiplets. So some of the specs we can get to is 150 terabyte per second, 2 gigabyte SRAM, and 9.6 petaflops. And then you can see some of the other specs here. So we finally get sufficient performance from the memory subsystem that the ratios are now matched, right? So in the 8-bit mode, the ratio is 16, and then of course the memory bandwidth scales as the precision drops. So the arithmetic intensity that this architecture supports is 16. So what happens because of that is if you plot model size plus context length on the x-axis, and then throughput or latency on the y-axis. So as long as you can fit everything within SRAM and you can scale out using mini cards, you can get this really high SRAM bandwidth, and that's where you see the best performance. And if you're not willing to put as many cards, or if the model is very big, you start spilling out of SRAM into DRAM subsystems, and then you get a lower bandwidth. So you try to get a performance mode where you get everything is served out of SRAM and you get much better performance, or you get a capacity mode where if you want to use very few cards or your model is very large, but then the performance drops. So that's how we are segmenting the product.
So Steve, the question for the 2 gigabytes there, how many of those are in-memory computing EMC micros, and how many of those are regular global buffer SRAMs?
About 75% are in-memory computing, and then the remaining is the global buffer for activation, holding, and all that.
And for the SIP unit, is that also customized accelerators, or is that a vector engine fully programmable?
It's a vector engine that is fully programmable. So on this generation, we started off with a 10 silica base, and then we added like around vector instructions on top of that for exponential or things of that sort. But now the RISC-V ecosystem has caught up, and so we're looking at RISC-V to see the trade-offs there.
As a EMC is only supporting MX integer, but the vector, the SIMD engine supports just regular all the fully.
That's correct. So the SIMD engine is traditional FP16 or bfloat16. Some of the RISC-V extensions today, the vector instructions also looking at FP8. So those are straightforward precisions, because the SIMD operations don't bottleneck in precisions, it bottlenecks in something else. But the matrix math, you want to do it in as low precision you can get away with.
And each cluster has a Q4 or quad-core RISC-V?
So each cluster has a quad-core RISC-V.
And those are, like you mentioned, mostly just for like manipulation, dispatching, synchronization.
Correct. So they're mostly for control plane offload. So all of the graph manipulation and the runtime runs there, and then you dispatch instructions to all of the compute units, either for compute or for data transfers.
Do you do any model operators on the scalar core, or they are all done?
The only model things that we do on the scalar core are any kind of decision-making type of stuff. If you have to branch in the graph, but all the data path is handled in the special purpose units.
Are you guys using your own CPUs for those like quad cores? No,
we are not. We licensed the quad core CPU in this particular chip from Sci-Fi. So it's the S76 CPU. So we don't see a lot of, I mean, we can add instructions to that, right? And we can customize it, but we're not.
At the chip that we're using, like you mentioned, the 74 currently is on Tensilica?
Yes, today it is Tensilica, but the next generation we are looking at RISC-V, because at the time when this was designed, the RISC-V vector instruction set wasn't quite ready yet. But it's at a point now where it's some useful things can come out of it. Plus the tool chains for the RISC-V is much better, right, than some of the other tool chains.
So the EMC modules are writing to the SIMD vector registers directly?
No, there is something called an output buffer, and so it writes into that output buffer, and then the RISC-V's, whatever, the SIMD engines pick up from the thing as a vector load. Yeah. Okay, so I will hand it over to Ayush for Scaleout.
So in the next section, we will.
Ayush or Sudeep, there was a question on the chat. What is the?
Akhil, I think you were saying something.
Oh, sorry. Can you hear me?
So in the next section, we will look into Scaleout. So running models on multiple devices. So in what Sudeep talked about was what a single chiplet looks like. A single chiplet has a specific capacity of, let's say, how many model parameters it can fit. More often than not, because LLMs are pretty large, they require multi-device execution. So we'll just go over a toy diagram of what partitioning, specifically model parallel partitioning today looks like across multiple cards. The same concepts hold across GPUs or accelerators. So this is a toy diagram of transformer layer. We have LRN here for layer norms, attention, projection, feed forward 1, feed forward 2. So with a couple of, one way of partitioning such models is what is called intra-operator partitioning. So we take, let's say, each operator, we shard it horizontally. Also, many papers call it as tensor parallelism. So we'll just use the notation TP here for tensor parallelism. So this way we partition a layer across 2 cards. Now, if we have more cards, another popular approach of partitioning is also pipeline parallel partitioning, which is inter-operator partitioning. So say you took a transformer layer, mapped it across 2 devices. You took another transformer layer, mapped it across another set of 2 devices. So in this toy diagram, what we are showing is, okay, we have 2 layers, which have been mapped on 4 cards in a tensor parallel 2 ways, pipeline parallel 2 ways. That's just a notation here popular in the literature. So this could be extended for any number of layers, right? And each layer could have different requirements. Say a layer is sharded in the tensor parallel way across 4 devices or so. Now, typically, the implication of partitioning a model is shown here in the toy diagram below. So each operator gets partitioned. So each device gets a partition of an operator and a few operators, as shown here. But more importantly, this introduces inter-device communication. And broadly, we can classify them into 2 categories. So collective communication. So all reduce here is one of the collective communication. The key point is that these operators involve communication across multiple devices. So say if this layer was being sharded horizontally across 4 devices, all those devices would participate in this inter-device communication. In this case, let's take the case of all reduce. And the second type of communication, or these yellow boxes here, are for pipeline parallelism. So when we create pipelines between layers or groups of layers, right, these are traditional peer-to-peer communication, send receive. So when we're running a model, let's say partitioning this way on a GPU or an NPU, typically what would happen is we would have 4 such instances of models running on 4 different devices. And the communication between them, either collective communication or peer-to-peer communication, is what orchestrates the entire model's execution. So we'll zoom in a little bit more on the collective communication aspect. That is a pretty expensive phase, especially when we try to partition a model across a large number of devices. We'll not go into the details of the algorithm here itself, but we'll try to motivate what our solution is by looking at this cost function. So ring-based collective implementations are fairly common. And there's 2 key aspects of this equation. The factor L, which is what comes from the link latency. And the second term here, which depends upon the bandwidth. So link latency and link bandwidth, we can abstract a typical interconnect based on these 2 parameters. For collective communication, which are implemented using this ring-style algorithms, right? The key point to notice is the bandwidth component is rather independent of n. N here is the number of devices. So this is good. Let's say if we had large tensors, right? We are moving megabytes of data over traditional, let's say, interconnects, right? The first factor is pretty small. The large tensor, the tensor size the second term would be the dominant term. And notice that it is rather independent of n. So this works good for large tensors. However, the bad part is the latency component. Latency component grows linearly with n. So let's say if we took a transformer layer, partitioned it across 16 GPUs, and still end up using ring-based implementations for implementing collective communication, especially in the domain where the tensor sizes are small, which is characteristic of token generation phases in LLM, the communication cost is dominated by the first term, which is linear to n. And an alternate implementations are what are called one-hop tree-based implementations. We'll skip the algorithmic details, but we'll look at what the cost function looks like. So the key aspect here is compared to the ring-based implementation, this makes the latency component constant with respect to the number of devices. So these algorithms, the bandwidth component is also independent of n. The latency component is also independent of n, so which makes it suitable both for large and small tensors. And the large tensors, majority of the models like CNNs, prompt, BERT-like models have large tensors. Token generation, which is really the bottleneck phase of LLM, they have small tensors. So with this background, we'll motivate like what specific problem we went on to solve in Corsair Scaleout. So as we noticed, high bandwidth favors collective communication on large tensors. This is very common, like in the summarization or the prompt processing phase. So this is a must-have. And the high connectivity, this favors collective communication on small tensors. And high connectivity, or in other words, either fully connected topologies or hierarchically fully connected topologies. So this is desirable for things like token generation, right? However, typically, fully connected networks are very hard to scale. So say if we have physically fully connected networks, the cost of wires and routing would be too high, especially, let's say having 4 fully connected devices is rather easier compared to 16 devices which are fully connected. So the number of wires just grow exponentially with the number of devices. And likewise with logically fully connected topologies, right? Let's say if we have a switch where we are able to connect multiple devices, again, these are also hard because one are the two factors. Typically, the cost of bifurcation at the endpoints of the devices is high, and cost of building switches, which can support a lot of devices, is also high. So in general, having scaling fully connected network topologies, although it's desirable from the workloads characteristics, it's very hard to scale in hardware because of the physical cost of implementation. So the way we solve this in Corsair is through hardware-software co-design. We, from hardware, we provision high bandwidth and fully connected topologies until 16 chiplets. So if we are able to, let's say, map a model using tensor parallelism across 16 chiplets, these enjoy high connectivity and hence low latency. And from the software side, we construct our collective communication using the one-hop tree style of inter-device communication. And then we also look into approaches of how do we hide communication behind computation, because that's a key goal. Can we make communication cost small enough? And can we hide communication entirely behind computation? Because that is what would help us make sure that our chip is running at high utilization. So we'll zoom a bit into both of these. How do we achieve it in the current Corsair product? And with doing this, our landing zone becomes tensor parallelism until 16 chiplets optimized for small tensors. And this helps us tremendously in the token generation phase in LLMs. And when we scale beyond the 16 chiplets to multiple cards or multiple nodes, we use pipeline parallelism. So pipeline parallelism typically is not very expensive because it's peer-to-peer communication, as opposed to collective communication where lots of devices have to participate. So the volume of tensor moving over a network is much higher.
So each card has 8 chiplets.
Each card has 8 chiplets, yeah. So let's zoom in a bit more into what we did into the hardware and software to achieve the landing zone. So we'll briefly introduce die-to-die link. So die-to-die link is our custom interconnect. As Sudeep showed, this is a logical view of one card. It has 8 chiplets. Specifically, this blue, one of the blue arrows here is what is a die-to-die link. Specs-wise, it supports 64 gigabytes per second unidirectional bandwidth. It's a full duplex link, so if we are counting for bidirectional bandwidth, it's going to be 128 gigabytes per second. It achieves very low latency, about 40 nanoseconds, and high energy efficiency. Now, what this motivates us, because the latency of the interconnect is small, we're able to make sure that, especially in the small tensor size region where the latency dominates, we're able to optimize for it. And second, and other aspect is because the energy efficiency is quite high, we can afford to have many die-to-die links per chiplet. Now, typically, as Sudeep showed in our chiplet, we have multiple die-to-die links. We can use it in one of the two manners. Either multiple die-to-die links in a chiplet can be ganged together to form an interconnect with higher bandwidth, or they can be used independently to connect to more number of devices for more connectivity. So typically, it's a trade-off between the two. How do we right-size it for both high bandwidth as well as high connectivity so that we can optimize it across the suite of tensor sizes, small, modest, and large tensor sizes. So now that we have a die-to-die link, here we show the physical construction of how 4 chiplets connect together. So 4 chiplets, we have a forms a multi-chip module or a package, right? So these are the 4 chiplets shown here. These are fully connected. So within a package, 4 chiplets fully connected. This is specialized for low latency collectives, especially in the case where the tensor size is small. And we have 2 die-to-die links between a pair of devices. So that gives us a unidirectional bandwidth of 128 gigabytes per second. Now, each card is physically comprised of 2 packages. So each of these blue boxes shows a package here. And these packages are connected through PCI link, which we'll discuss next. So this shows us how do we scale from a single chiplet to multiple chiplets in one package. We use a similar methodology to scale to multiple packages as well. So now in this construction, there are 2 cards, so card 0 and card 1. Each card consists of 2 packages, as we saw in the previous slide. And the goal is to be able to connect these 4 packages also in a fully connected manner, again, to optimize for low latency for collectives. So, and we achieve this using PCI links. So we'll go over how the PCI links are connected. So these red lines are a couple of PCI links which connect the packages within a card. Then these purple arrows are what we call PCI links, but they connect over a bridge connector. So the red lines here, these are traces on the PCB itself, versus these purple lines, they are connectors exposed on a PCI card, which are connected over a bridge connector. So using these, both the red and the purple lines here, we have 4 packages in a fully connected topology. And beyond this, to connect multiple cards or subsequently multiple nodes together, right? These cards connect to PCI switches for either connecting to other cards or to host. And this is how one card physically looks like, right? So as we discussed, this has 2 packages here, each with 4 chiplets, packages for the LP5 DDR. On the bottom side, edge connector, which connects to PCI switches. This line here, that's the internal PCI link on the PCB itself. And these connectors here, which can be connected to another card through a bridge connector, which realize these purple links here. So far, this scales, as we discussed, until 16 chiplets. So 4 packages with 4 chiplets each. And this is highly specialized for tensor parallelism, especially in the small tensor size regime. Now scaling out to multiple cards. So we have 4 such PCI cards connected to one PCI switch, right? And notice that this bridge here is what we are referring as a bridge connector. So a pair of cards are specialized, and multiple such pair of cards connected through PCI switch and PCI fabric. So in this way, we can scale inference for models, let's say, which require more than 2 cards, right? By mixture of doing tensor parallelism and pipeline parallelism, where it makes sense. And inter-card communication over, so when we have to communicate over PCI switch, typically the latencies are higher, the bandwidths are lower, because notice that a card on this PCI switch talking to another card on this PCI switch has to go over a shared link. So there's the lower bandwidth, higher latency. So this is typically acceptable for pipeline communication because they have low bandwidth needs. It can also work for tensor parallelism when the tensor sizes are very large. For example, the tensor size is on the order of hundreds of kilobytes or megabytes of range, like what we see in prompt processing, right? So either we bump up the sequence length or the microbatch size, then that makes the latency component rather less important. So those cases of scaling tensor parallelism, we are still able to leverage. And when we communicate, so for models which even span, so this is one inference node comprised of 8 cards. For models which span multiple nodes, again, we can leverage pipeline parallelism, and this will be through traditional interfaces like RDMA over Ethernet. So that showed our scale-out story for the Corsair hardware. Let's look into the software techniques, the algorithmic techniques that we use to map collective communication on our scale-out hardware. So there are two key insights that we piggyback on. The first insight is now because we have specific domains of fully connected hardware topology, we can construct hierarchical one-hop trees. And as we saw before, one-hop trees compared to ring-based implementations have much lower latency, which is important in the small tensor sizes zone. And the second insight, and we'll illustrate this with an example, is interleaving phases across hierarchical collectives to minimize any redundant data movement. So we'll go over both of these insights with an example of all reduced between 16 chiplets. So 4 packages connected over PCIe, and 4 chiplets in each package connected over the die-to-die interface. So in the first insight, let's say we construct a all reduce between 4 chiplets in a package. So typical decomposition of a all reduce can be thought of as a reduce scatter, and we'll go over what that means, followed by a all gather. So we can think of this as like, let's say we have 4 chiplets, chip 0 through chip 1 in a package. And let's say each chiplet has a tensor which is partitioned into 4 ways, so 4 chunks. So this specific blue box is A0 through D0, shows the 4 chunks of the tensor on chip 0. And within a reduced scatter, all the other chiplets send the first chunk to this chip 0, which performs the reduction. So in parallel, this will happen for each chunk on all the other chiplets. So at the end of this reduced scatter phase, chip 0 would have 1/4 of reduced tensor, chip 1 would have the next 1/4 of the reduced tensor, and so on. So this is what we typically refer to as reduced scatter. And following this, we can think of all gather, where chiplet 0 sends its reduced chunk to everybody else. Everybody else is doing it in parallel, and that's what we call as all gather. So this construction is typical. So all reduce split into a reduce scatter followed by an all gather phase. And this we are doing here for 4 chiplets in a package. We can think the exact same way between the 4 packages here, right? So again, there is a reduce scatter phase where let's say C40 here refers to chiplet, one of the chiplets. So these C40 through C43 are the 4 packages. So each package is reducing 1/4 of a tensor and post-reduction, sending it to everybody else. So split into 2 phases. So these are the 2 hierarchies of interest here. The hierarchy between chiplets over die-to-die, and the next hierarchy built over PCIe between the packages. And the insight 2 is interesting. It talks about now when we layer multiple such hierarchies together, there's a potential for optimization. A naive way to construct this could be, okay, we have a reduced scatter over die-to-die, followed by an all gather over die-to-die, subsequently a reduced scatter over PCIe, followed by an all gather over PCIe, and lastly, it requires post-collective like broadcasts to make sure every chiplet indeed gets the final output. We can interleave some of these communication phases to minimize redundant data movement. One such interleaving is shown here. So let's say we do a series of reduced scatter across the entire hierarchy. So reduced scatter across hierarchy 0, reduced scatter across hierarchy 1, and then we start backtracking, all gather across the last hierarchy. And this could extend to, in general, any number of hierarchies. So we start from hierarchy 0, go through hierarchy n-1, and then backtrack, doing all the all gathers in the reverse order. So this is what is shown here as well, right? So the first and the fourth phases were the respectively reduced scatter over and all gather over hierarchy 0, right? So using these 2 insights, we are able to form one-hop tree-based algorithms which map pretty well to our fully connected topologies. And because by construction, we create symmetric hardware topologies, we are able to minimize certain data movement. Overall, using these two techniques, we are able to reduce the cost of collective communication quite significantly. Yeah.
The second A slide.
Yeah.
The reason it's better to do basically finish all the reduce
Mhm.
before we gather
Mhm.
is because the traffic is a pattern or straightforward, and you need directional traffic instead of mixing traffic.
Correct. So for example, in this case, let's say the end goal is to do all reduce between all 16 chiplets. So that's why we can layer it this way, that reducing within a package and then reducing between packages and then start doing all gathering. But versus, let's say, if there was a alternative partitioning, let's say where between chiplets, it's partitioned such that it requires collective 0 versus between packages, it's a different axes of partitioning requiring collective 1, then this technique may not be applicable. But in many cases, because let's say n NPUs, just because one couldn't have n fully connected devices, there's a hierarchy, right? So it fits well in many of those topologies. And this is further illustrated in this diagram. So let's say this shows x-axis here is chiplets within an MCM, y-axis is packages across cards, right? Phase 0, each of the package does its own stuff. So after phase 0 or the reduced scatter at hierarchy 0, 1/4 of the tensor is reduced in each chiplet in a package. Notice it's not yet reduced between packages. We can further extend this, right? Now in the next phase, all of these blue chiplets participate, right? And now these are the final reduced values across 16 chiplets. And then we do the all gathers to eventually realize the entire collective. So that's the first part of it. The one-hop tree will discuss briefly about partitioning. So what one-hop tree construction on fully connected topologies and the interleaving gives us is we're able to reduce the cost of communication quite significantly. But ideal is to make sure communication is free of cost. At least that's the wish list. So we looked at techniques to partition such that we can efficiently get the compute communication overlap. So these two approaches, this again shows a baseline transformer model. One of this, these are two popular partitioning strategies, Megatron cell partitioning, invented by NVIDIA. So here, alternating layers, we follow there's an alternate pattern of column-wise and row-wise partitioning, right? So for example, these matrices are partitioned column-wise, these matrices partitioned row-wise. It introduces this all-reduced collective. There's an alternate partitioning style where, let's say, each matrix was partitioned just column-wise. So it introduces the all-gather collective. Now, the key aspects why we explored partitioning, different partitioning techniques is all reduces specifically in token generation can only be overlapped with the preceding operation, right? So for example, this all reduced just with this projection versus all gathers can be overlapped with a longer chain of preceding ops. So that helps us to hide so because the margin of compute or the budget of compute to overlap with is higher, high likelihood that we'll be able to hide either all or most of the communication cost, right? So that is one insight. And then bit precision requirements, typically collectives that involve reduction have higher precision needs, like 16 bits or higher to make sure we don't degrade accuracy. Collectives that involve only data movements, that can be done at reduced precision. And resource collision, again, collectives which use reduction require SIMD, all gathers don't. So these are some of the alternate partitioning strategies we look into. Putting both of these two together, we were able to make sure that bulk of the collective communication can be hidden effectively behind compute. So this helps us achieve high compute utilization. Okay, we'll next transition to Akhil.
Okay, thanks, Ayush. Can you guys hear me? Can you confirm if you can hear me?
Akhil, can you hear us? I think the audio is breaking.
I can hear you, but you're not able to hear me, is it?
Okay, I can hear you on the phone.
We can't hear you, Akhil, still.
How about now? No.
It's broken.
So I'm getting some feedback from the room, but others on the bridge.
Should we try different audio?
Yeah, maybe try your speaker, but I don't think that works.
Right.
Say something again, Akil.
Yeah, can you hear me better now?
Well, let's switch back and say something again.
How about now?
Okay, this doesn't work. Let's just use the speaker.
Sophia, I think Akil was pointing out
Okay.
that there were some questions in the chat.
Okay. Akil, can you say something again?
Yeah, can you hear me?
Okay. Can folks in the room hear the room? Akil, keep talking.
Yeah, sure. Can you guys hear me? Just
It's reasonable at least. Okay, let's use this. I assume you already maximize the volume at this point, and we'll see.
okay.
There it is.
Okay, I'll try to speak up.
Okay. Okay, go ahead, Akil.
Okay, sure. Yeah, thanks. Okay, so far I think we've got an overview of what we've been doing from the lower levels of the stack, starting from circuits to chiplets to scale-out hardware and scale-out algorithms, right? So now I'm going to go a little bit higher in the stack to talk about our software stack. Oh, could you switch slide, please, Ayush? Yeah. So this a block diagram of what our stack looks like. We don't need to go through the whole thing, but the key things to notice here are we maintain a known entry point that we want to keep to for the users, and that is through what we call our model factory, and then that feeds into our compilation stack. I'll go into a little bit of that. And this is comprised of our quantization tools and our PyTorch front end and a graph compiler mainly. And we also have ways to write optimized kernels as well. And along with the compilation stack, paired with that is our execution stack. With the execution stack, so essentially the artifacts that are generated by our compilation stack is consumed by our execution stack. So today I'm going to spend a few minutes on the compilation stack and some more time on the execution stack. Can we move one slide, please? So if we look at our compilation stack considerations, right? So we're a accelerator where we have a lot of the programming responsibility is shift to the software. Things that are done for us in the GPUs, for example, things like scheduling. So mapping and scheduling are both software responsibility here. And if you recall, so everything that we've done on the hardware levels are to be able to deliver extremely low latency inference. So a key part of being able to do this means that we need to, not only do we need to optimize for data movement everywhere through the chip, collocate the compute and the data very, very, very diligently. And along with that, we need to also avoid repeated trips to the host. So that is for that leads us to graph-based compilation. And then we on the accelerator, communication can be a bottleneck, just like what Ayush mentioned, right? About overlapping collectives with compute. We need to employ aggressive operator fusion, not only between collectives and compute, but other operations as well. So these are some things that the stack needs to be able to do. One more. And then, of course, integrate with existing frameworks. So for this, we expose a familiar abstraction that is a card. And at the same time, we need the ability to compile the workload to multiple cards. So for this, we adopt a hierarchical compilation or lowering strategy. And next, please. So another key point in LLM inference, especially, is dynamically changing tensor shapes. So with auto-regression, some of the key tensor shapes are increasing by 1 every token iteration. So this means that this kind of does not pair well naturally with graph compilation, right? So for this, we need to support sort of late binding of some shape resolution, and we need to support this at runtime on chip. One more, Aish. And then, of course, the community is innovating at a rapid pace. So various optimizations are coming into these workloads every week or so. So we need to be able to keep up with this with high performance kernels that we can develop or we can leverage from that has been developed by the community. So these are some of the considerations there. Now, moving to the execution stack, here is a picture of our execution stack. Now, before I'll briefly walk over this. On the right side is our cluster. We call this Aviator Inference Engine, Aviator IE, Aviator IE cluster. So this cluster is essentially a set of cards and the associated software components that are required to run distributed inference on these set of cards, right? And then on the left of that is the Aviator IE user process. So this would be something that interacts with the customer side of the workload, where, for example, you have an inference server from the customer, and then that is aggregating requests. So then that would we would receive inference requests from there, and this goes through our LLM specific wrapper that does things like tokenization, etc., and goes through our distributed inference orchestrator that manages the multiple cards that are participating in the inference and then enters our cluster. So going into more detail here, the host runtime and the inference engine form the main components of our stack, and those are indicated in green and blue here. And some of the things that are worth noting here is the green, especially, right, is split over multiple levels in this picture. I'll come back to that in a minute. And for now, let's move to the next slide, which talks a little bit about our runtime. So this our Aviator runtime, this provides an interface to the external world to a single card. So this means that again, the low latency requirement of our card means that we need to prioritize decoupled or asynchronous execution. And how we view this as is, so basically the host generates as much work as possible, as fast as possible, and the device consumes as much work as possible. So that they operate in a decoupled and asynchronous manner just by through things like sort of like a queue or a table structure, just to denote that here is the work and here is the completed work. Can we move forward, Aish? Thanks. Now, talking about the inference engine, right? So again, to keep with our low latency requirement, we need to avoid centralization as much as possible. So this is where we differ a little bit from other inference engines. So Ayush, one more step. Yeah, so you can see that our scheduler and memory manager is something that we have at each card, right? So we need to move our. We've decided to move our scheduling and memory management decision closer to the device, keeping with the ability to serve inferences at low latency. And the next piece is we need to support pipeline parallelism. We noticed that when we surveyed the landscape of inference engines, pipeline parallelism was not commonplace. And we, on the other hand, we want to be able to support pipeline parallelism. So our scheduling and memory decisions are done at a pipe stage level, at a pipeline stage level. And for this, we exchange control information between pipe stages to enable this. So if you think about it, while all of this software is running on the host and only control messages are being passed between the processes that are attached to a card, right? However, data always moves on the backplane or on the backplane from card to card or chiplet to chiplet directly. The host does not get involved in most of the data movement from a data plane perspective, other than the input and output, right? Okay, so that's a little bit about our software stack. Next, I wanted to briefly give an intro to go one level higher in the stack again. So this is a piece of work we did recently where we we focused on the model architecture. So again, with the view of helping inference performance. So this work was led by Mohammad Adnan, who was an intern with us from UBC, and it was a collaboration between us and Adnan and Adnan's advisor, Prashant Nair at UBC. So this is going to appear in MLSys 2024, and this work is called Keyformer. So here, the main idea of this work is to see we propose a inference time attention sparsification technique. So how can you sparsify attention? Knowing the fact that KV cache is the dominant consumer of memory bandwidth and it's a performance limiter, right? What can we do about it? That's what this addresses. Ayush, next slide. So yeah, like we talked about earlier, right? As sequence length or context length grows, your KV cache size grows. That's shown on the right here. And if you look at the inference time, so a lot of the time is consumed by KV cache operations. So this was done for MPT 7 billion parameter model and with on an NVIDIA A100 GPU. And Ayush, can you move forward one slide, please? So this problem has been looked at in the academia and industry before, right? There are techniques such as GIST tokens or landmark tokens, which try to reduce the context that is fed into the model. However, those require fine-tuning or retraining. Then there are other techniques where you just try to discard some tokens at inference time, for example, window attention, and so on. However, we found that those would not keep the model quality as high as you would expect. Ayush, one more slide. So now, few key insights from our work here is that there is sufficient sparsity that's available to be exploited. So if you look at attention scores, a lot of it is zeros. So on the left here, you see across the layers for the three models, the different level of sparsity that's available. And on the right here is where you see what is the it's a CDF of the cumulative attention score. So 90% of the attention score is distributed across just 40% of the tokens. So this allows us an opportunity to exploit this to store only these key tokens potentially. However, Ayush, one more step. Next slide. Yeah, we cannot do this. Naively, right? So what happens is when you drop tokens, the distribution of the scores changes, and hence that affects the model quality significantly. So you need to account for this. Yeah, one more slide. So for this, we propose Keyformer, where the idea is that we maintain some of the recent tokens and key tokens from the past context that we attend to. Next slide. So the idea here is that we drop the tokens which have a low score. Those are shown in the X's in this picture. And in the next iteration, another token would get dropped, right? And one more step, Ayush. Now, if you look at the decoder layer, what we do here is one more step, one or couple more steps. Yeah, few more steps, please. Yeah, we need to account for the distribution distortion that we caused because of the tokens being dropped. And we do that by regularizing with a Gumbel distribution or using a Gumbel softmax. And this we use to account for how we choose new tokens to drop. And this is a high level of the technique. And then next slide, please, Ayush.
A time check, 3 minutes.
Yeah, thank you. So yeah, I'm just going to speed through this. With all of this, so we can meet a very high accuracy bar of 99% of the full attention with this technique across the different models and different tasks. And Ayush, one more step. And with a long context, for example, right, where your KV cache starts to dominate, then you can see that you can achieve a speed up of about greater than 2x in scenarios where you have like a 8K context. Okay, so I think I'm going to stop here. So I know we ran very close to time, but any questions?
Okay, great. Let's thank our speakers. Do you have time to take 1 or 2 questions? Any questions for the speakers?
So like for this Keyformer work, for example, did you guys have to like change the hardware significantly to support this? Like you already have like a SIMD unit and the matrix unit. Was that like general enough that all the changes were just software?
Could you hear the question?
Yeah. So for the Keyformer work, this work was all done on NVIDIA A100 GPUs. So this work has not yet been ported to our hardware. This was just algorithmic work that was done on NVIDIA A100 GPUs.
Okay, but when you port it to your own hardware, you expect it to just be software changes, like
just be software changes. We have all of the hardware necessary to do things like the Gumbel softmax, etc., on our chip. So Kenneth asks, has the system been implemented? Yes, it's been implemented for the GPUs and the code is open sourced.
Okay, great. We are also at the time. Let's thank our speakers again. We do have a student meeting happening right now in the Slice Lab in the Arch room. So if you're interested in talking to the speakers, follow, I guess, the sound in the comment. They will lead you to the room. Well,